Today we're going to be talking about alternating series. So when a series is going to alternate between two numbers. So our alternating series test. An alternating series, okay, where you have to look for this -1 to the nth power. Okay, so look for when you have a -1 to some power. That's going to kind of give you a hint that it is an alternating series. And it could be n+1 if you want it to be, okay? And then everything else in the series part is going to be our a sub n. And that's really what we're going to be dealing with. So our alternating series test. This converges when the two conditions listed below are met. So the limit has to go to 0, and your a sub n+1 has to be less than or equal to a sub n for all n. Okay, and we're going to have to prove this one. I kind of did a poor job of proving this in past years. I'm going to hold this a little bit more accountable this year. And understand that this converges when these two conditions are met. Okay, you can't really use this to say this series diverges. We're going to come up with there's going to be an example where we're going to look at this and it's going to diverge, but we're not going to say it diverges by the alternating series test. Okay, this only tests for series that converge. Okay, so determine if each series converges or diverges. Okay, so for the first one, take the limit as n goes to infinity of 1 over n, and that equals 0. Okay, so my first condition, popping back, my first condition is met. And now I need to prove that the n+1 term, so the n+1 term is always less than or equal to 1 over n. Now, n are positive numbers, so I can cross multiply. Okay, and then if I subtract n from both sides, we get 0 is less than or equal to 1. That is a true statement. So you've stated both conditions. You've stated condition 1 here. You've proven condition 2 here. So then we can say that this converges by the alternating series test. Okay, our second example here. So I take the limit as n goes to infinity of this n+1 over n, and this ends up equaling 1. So this diverges, but not by the alternating series test. This diverges because this limit of this series went to 1, and that was the nth term test. And yes, I understand that it is alternating here. Okay, you keep popping between different numbers, but you can look at this piece and prove that that diverges. Okay, alternating series test remainder. So basically when you're summing up all of the terms, okay, so first of all, we have to be a convergent alternating series, okay. The absolute value of the remainder, what's left over after I've added all the terms, okay, is less than or equal to the first neglected term. Okay, so say I'm summing up, so S is standing for the actual sum. Say I'm summing up the first 6 terms. Okay, this is going to be the remainder, what's left over. Okay, so the actual sum minus my sum of my first 6 terms is going to be found in our 7th term. Okay, what's actually how the actual sum differs from the sum of the first 6 terms is found in this 7th term. Okay, approximate the sum of the series by the first 6 terms. Okay, so first you have to prove that that it converges. Okay, and we know that if I were to plug in n plus 1 to the 3 halves, that this is going to be less than or equal to just n to the 3 halves, because smaller denominator, okay, I'm sorry, larger denominator equals smaller overall number, okay, and that's an and there. The limit as n goes to infinity of this equals 0. Okay, so now what we have to do is we have to find the sum. So I find the sum. -1 plus 1 over 2 root 2 of the first 6 terms. I was thinking about a 6, so I wrote a 6. Okay, so what this is, and I found this in my calculator, is this sum of the first 6 terms zero, 3, 5, 2, 9, 8, 0, 3, 6, 5. Okay, so what that means is the actual sum of this series minus the sum of these 6 terms is going to equal what my remainder is, okay, what I have left over, and that kind of makes sense, and that's less than or equal to my 7th term, which is 1 over 7 to the root 7, times root 7, I should say. So my sum minus the sum of these 6 terms is less than or equal to this 1 over 7 root 7. Well, this is really just an inequality from algebra 1. So you have the negative root one over my positive root. And from here, it's just calculator work. I'm not going to show you guys that calculator work because you guys know how to use your calculators. But you should get this. Okay, so the actual sum is going to be somewhere in between these two numbers. If you think about it, the more and more terms you add, the closer to the sum that you're going to get. Okay. All right, the next example. Determine the number of terms required to approximate the sum of the series with an error less than 0.001. So what I do is I take the nth term. Okay, and this has to be less than or equal to 0.0001. Since it's the absolute value, that's why I kind of ignore this to the -1 part. And I solved this inequality, so I went through the math and I solved this. So I multiplied by this 2 to the n plus 1, since I know that's always going to be positive, and I divide out that 0.001. I added too many zeros in there. So I divide that 0.001 over to the other side and get 3,000 less than or equal to 2n plus 1. I wrote this then as, and I divided out 1,500 less than or equal to 2n. So what I did in my calculators, I just looked at a table of values, and I looked for when is this value, when is 2 to the n going to be greater than 1500, and that happens at n equals 11. So I just did this in my calculator. Okay, I guess you could do a log if you wanted to, but I just looked at when 2 to the n, 2 to the So 2 to the, where's my marker? There it is. 2 to the 11th is 0.248. 2 to the 10th is equal to 1024. So this is where my error happens. Okay? Okay, absolute convergence, and then conditionally convergence. Okay, so a series converges if the absolute value of the series converges. Then we know the series without the absolute value signs also converges. So a series is said to be absolutely convergent when the absolute value of that series converges. And a series is said to be conditionally convergent when the absolute value diverges, but the original function converges. Okay. Okay, this problem always scares me. I don't know why this problem always scares me every year. This is not that bad of a problem. Okay. Determine whether or not the series is absolutely conditionally or absolutely convergent, conditionally convergent, or divergent. So what you want to look at first is let's look at the absolute value. So we're going to look and see if the absolute value of this series converges. And I don't know why this always freaks me out every year. Let's look at this. Cosine of n, or the absolute value, I should say, of cosine of n over n squared. Well, we know that that's going to be greater than 0, but this is going to be less than 1 over n squared. Okay? Because cosine is going to range from, the absolute value of cosine is ranging from 0 to 1, essentially. Okay, so I'm going to compare this. So what I'm doing is I'm doing the direct comparison test. So I'm going to compare this series to this series, which converges by the p-series test. P in this case is equal to 2, which is less than 1. Okay, so therefore, this converges by the direct comparison test. Okay, so therefore I know that this is absolute. Oh, I really spelled that wrong. Absolutely is absolutely convergent, or converges absolutely. Okay, now this one. Okay, what I look at is I look at, again, the absolute value of this series which that equals this series, because the n's are always going to be greater than 1, with the absolute value, that's going to take away any negatives you would have. Okay, so this converges by the p series test. P is greater than 1, so therefore, again, this one also converges absolutely. Okay, last example. Okay, so now we want to look at, again, what I do is I look at the absolute first, which is going to equal this series. And now I need to determine whether or not this series, okay, is convergent or divergent. Well, remember we have all these different tests, but the first one, the one that I always forget about, that you always want to check first, is the nth term test. So take this limit, which equals 1/3, this diverges. Okay, so it's not absolutely convergent. So then what I look at is could it be conditionally convergent? Could I look at that, and is that, without the absolute value signs, okay, could this be convergent? And it's an alternating series, okay, so I do my alternating series test, and again, I look at this, and that again equals 1/3. We have that work here, so this diverges, okay, and I would say it diverges by the nth term test. Okay, because the alternating series test essentially kind of fails. We know it's not convergent, but we can't use the alternating series test to say something is divergent. We can only prove that it is convergent with that test. Hopefully that makes sense. Okay, so there was a lot in this lesson. We had our alternating series test, we had our error bound, and then we had absolutely unconditionally convergent. I hope you liked that video. I hope it was helpful, and please make sure you have everything ready for class.